Okay, so we are in Statistical Rethinking, second edition. We are on chapter 9 and question 9E3. So far in these questions that we've been addressing, we've looked at two different algorithms that could be used in theory, and have been used, and sometimes maybe are used, to solve Bayesian problems. Okay, and the first one we talked about was the Metropolis algorithm, and then we talked about the Gibbs algorithm, and now we're actually getting to what Stan uses, and therefore what the Rethinking package uses, and that is Hamiltonian Monte Carlo. Okay, so let me just say a couple of things real quick. So first, the book gives a decent overview of Hamiltonian Monte Carlo, but it's really just designed to give you just enough to have a working understanding of what's happening. Okay, if you wanted a little bit more depth, you could definitely see this book right here. Here's a link to this book, A Student's Guide to Bayesian Statistics by Ben Lambert, which has a very good overview of Hamiltonian Monte Carlo. And then if you wanted a little bit more depth, I might suggest two things. One is not a statistics book at all. It's a physics book. It's for lay people, which I'm included, which is The Biggest Ideas in the Universe by Sean Carroll, Volume 1, in which he goes through and gives a very good explanation of Hamiltonians, which is what Hamiltonian Monte Carlo uses. And then, so that's a very approachable text. And then if you want something a little bit more sophisticated and in-depth, you might track down some of Michael Betancourt's papers. So anyway, where are we at here? Okay, so the question is, what sort of parameters can Hamiltonian Monte Carlo not handle, and can you explain why? Okay, so as not to bury the lead here, I'm going to jump to the answer, and then I'm going to explain the answer. Okay, so the answer after all of this is on the Colab sheet is right here. Okay, the answer is HMC doesn't work with discrete parameters. Okay, so normally, like when we're in a regression, we might have these beta coefficients, and often those beta coefficients are normally distributed, or that the prior is that they are normally distributed. Okay, and the normal distribution is a smooth continuous function. Okay, and they could be other smooth continuous functions. Now, so a discrete parameter though might be something like the value of the parameter can only be 1 or 2 or 0 or something like that, like maybe a count variable or something like that. So anyway, so that's what we mean by discrete parameter. And so now I'm just going to kind of explain why a little bit, okay? And give a little bit of background as to Hamiltonian Monte Carlo, okay? So HMC is a simulation of Newtonian physics, okay? Now the Hamiltonian itself is just a formulation it's just a way to write down Newtonian physics of motion, okay? So that's all it is. So the Hamiltonian itself is a function of momentum rho and position x, okay? And it is the sum of kinetic energy and potential energy, where kinetic energy is a function of momentum and potential energy is a function of position. Okay, so there you go. Now, in the context of Monte Carlo, what is going on here is, again, we're imagining some particle sliding over a multi-dimensional space, okay, and that space is defined by the parameters in our model, okay? It's defined by the posterior values or probability distributions of those parameters, okay? And actually, it's the log posterior values, and actually it's the negative log posterior values, right? So if you think about this, so think about a normal, so drop the log right now. So a log, when you take the logarithms of things, it just makes it makes some of the mathematical operations easier. That's why it's log. But if you think about a probability distribution, it kind of maybe looks like a bowl. And so if I take the negative of that probability distribution, or it looks like an upside down bowl, if I take the negative of that, Now it's a right side up bowl, and now I can imagine dropping a little bead in there and watching it slide around the bowl. Okay, and so that's why we take the negative log posterior space, right? So this is the thing we're simulating. We're simulating this particle moving around this multi-dimensional bowl. Okay, so with the Hamiltonian, again we have kinetic energy and potential energy, and if we want to track the progress of our particle, then we need to monitor how kinetic energy and potential energy are changing. Okay. And so in order to do that, we need the derivatives of the Hamiltonian, the partial derivatives of the Hamiltonian with respect to momentum and position. Okay. And it turns, well, this next part really is not important for what the answer is, but the next part is that it turns out that the partial derivative of the Hamiltonian with respect to momentum is just the change in position with respect to time. Okay. And the partial derivative of the Hamiltonian with respect to position is just the negative of the change of momentum with respect to time. And that's not really important. What is important is notice that the Hamiltonian requires, or solving the Hamiltonian, requires these different derivatives. And derivatives require continuous smooth functions. Hence, Hamiltonian Monte Carlo does not really use discrete parameters. Okay, so now the caveat. So it's actually possible to use discrete parameters indirectly. And the way that we do this is we marginalize the discrete parameters out. Okay, so what we might do then, so let's say that we had continuous parameters. We had several continuous parameters that we'll put in a vector called beta hat or beta arrow. Okay, vector of beta parameters. Again, these are continuous. And then say we have a discrete parameter which we'll call gamma. So if we're going to marginalize these out, okay, so we no longer want gamma in our expression, right? Because Hamiltonian Monte Carlo can't use discrete parameters. So what we do is we find that we take the joint probability of beta with gamma over each value of gamma. Okay, and so we sum across all of the gamma values. Okay, and then what we get is the probability distribution of beta. All right, so again we have the joint probability distribution. We sum across the discrete parameters, and then what we get is the joint probability distribution of just the continuous parameters. Okay, and so what this might look like then, so here I have two distributions for beta when gamma is at its first value and when gamma is at its second value. And so marginalizing them out, right, it's just summing them together like this. Okay, and so again, now all of a sudden what we have is one distribution for beta that has incorporated all values of gamma. Okay, okay, we'll call that good.